Okay, for today's lesson 2.3a, we're going to talk about a couple of different things today. First, we're going to talk about these things called higher order derivatives, and then we're going to follow that with another derivative rule, this one called the product rule. So regarding higher order derivatives, remember that the derivative of a function gives us another function. And if that's the case, then it should follow that we would be able to find the derivative of the derivative. And that's what we mean by higher order derivatives. It means you're finding the derivative of a derivative. Or maybe you're finding the derivative of that. So that's what we're going to look at first. So to illustrate this, we're just going to use a few different columns here. So notice on the first column here, we're going to put a function. In the second column, we're going to find the first derivative, which you just know so far as the derivative. And then, for the third column, we're going to find the derivative of the first derivative. So we call that the second derivative. And then if we wanted to, we could continue this pattern of finding the derivative of the previous derivative. Okay, so for this first example, we're going to deal with the function y equals x squared plus 9x. Well, the first derivative, as you just saw in yesterday's lesson, we can use the power rule and our basic derivatives. So we get y prime equals, okay, so derivative of x squared becomes 2x plus the derivative of 9x just becomes 9. So the first derivative of this function is 2x plus 9. So now, to find what's called the second derivative, we're going to find the derivative of the first derivative. Now, the first derivative was notated as y prime, so the second derivative is notated with y double prime. Now, the derivative of 2x just becomes 2. The derivative of 9, remember, goes to 0, so the second derivative here is just 2. Now, if I wanted to continue and find the third derivative, that would then be the derivative of the second derivative, and the derivative of 2 becomes 0. So the third derivative, if we were asked for it, for this particular function, would be 0. All right, let's do this for another function. So we have y equals the sine of x. Now, we would have y prime equals, now remember that the derivative of sine of x is the cosine of x. And then now, to find the second derivative, remember that the derivative of cosine of x is negative sine of x. Now, just to continue this, we're not going to write it, but just to think about, if I found the third derivative, well, the derivative of negative sine of x would be negative cosine of x. So the third derivative would be negative cosine of x. And then the derivative of negative cosine of x, well, that would just become positive sine of x, because remember, it's the opposite sign. So when we did the derivative of sine of x, that actually ended up sort of going in circles. Okay, now there's one more higher order derivative that's going to be an important application for us to consider moving forward. If we have a situation where we're dealing with a function, let's say it's maybe s of t, and that represents the position function. Maybe it represents the height of an object off of the ground at time t equals whatever seconds. Well, the derivative of position, well, remember, derivative is a rate of change. We just talked about that in the previous lesson. So the rate of change of position, the first derivative, is better known as the velocity. So the derivative of a position function gives us velocity, because velocity is the rate of change of position. All right, then that means the derivative of that, so the second derivative, so that would be s double prime of t, well, that's technically the first derivative of velocity. Well, again, a derivative is a rate of change. So if I'm finding the second derivative, that's now asking for the rate of change of the velocity. And for those of you who've taken physics, you might already know that that's referred to as acceleration. So the relationship between position, velocity, and acceleration is a classic application of this idea of higher order derivatives. Okay, so let's look at this first example here. So the velocity of an object at time t is given by the function v of t equals 20 minus t squared for t between 0 and 6, where v of t is measured in meters per second. Now, just a quick note, since velocity is being measured in meters per second, then that does mean that time must be measured in seconds. Okay, so the first part of the question, find the velocity and acceleration of the object at time t equals 3. All right, so we're trying to find the velocity and the acceleration at time t equals 3. Well, if I want to know the velocity at time 3, that means I'm looking for v of 3. Well, the function they gave us is v of t. So to find the velocity, I simply have to substitute into the velocity function that they gave me. So v of 3 equals 20 minus 3 squared. That's going to be 20 minus 9, which of course gives us 11 meters per second. So the velocity of this object at time 3 is exactly 11 meters per second. Now, if I'm trying to find the acceleration at time 3, that's when we need to remember that acceleration is the derivative of velocity. So acceleration at time 3 is the same as v prime of 3. Well, but that means in order to find v prime of 3, I first need to know what is the equation of v prime of t. So on the side, I'm going to just work that out very quickly. Remember, since v of t is 20 minus t squared, then that means v prime of t is going to be, well, the derivative of 20 goes to 0, and then the derivative of negative t squared becomes minus 2t. So v prime of t is just negative 2t. So coming back here to find the acceleration, again, that's the same as v prime of 3. So that means I'm going to take my v prime and evaluate it at 3. And that's going to give me negative 6. Now, if you don't know this, acceleration, because it is the rate of change of velocity, it's going to be negative 6 meters per second, which we would typically write as negative 6 meters per second squared. You do want to make sure that you're familiar with how to do correct units for position, velocity, and acceleration. Okay, so that's the velocity and the acceleration of this object at time t equals 3. Now, a natural follow-up question, and you won't necessarily have questions on this on the assignment, but the AP exam is sure to include these ideas in some of their questions. So now that we know the velocity and the acceleration at time 3, here's a follow-up question. So at time t equals 3, is the object speeding up or slowing down? Explain. And by the way, anytime you're asked to explain, that does mean to explain in words, as opposed to justify, which could involve words, or it could just involve showing your mathematical work. So explain does specifically mean that we need to use words to explain our answer. Okay, so at time 3, is the object speeding up or slowing down? Well, if you didn't already know this, velocity and acceleration could be positive or negative. And a positive or a negative sign does indicate direction. So imagine motion along just an x-axis, meaning we're only either able to go to the left or to the right. So having a positive answer might indicate we're moving to the right. Having a negative answer might indicate we're moving to the left. So to determine whether an object is speeding up or slowing down, we have to pay attention to how the signs of both velocity and acceleration compare. So in this particular instance, notice that velocity at time 3 is positive, but the acceleration at time 3 is negative. when velocity and acceleration have opposite signs at the same time, it means that the speed of the object is slowing down. So we can answer this question by saying the object is slowing down. And it does say explain, so I'm going to say because v of 3 and a of 3 have different signs. One of them is positive and one of them is negative, but it's not necessary for us to get more specific than that, because all that matters is that v of 3 and a of 3 have different signs, and our work above justifies that statement. Now, if velocity and acceleration at a time had, if they were both positive, or if they were both negative, if they had the same signs, then the object is speeding up. Now, sometimes people do get thrown off by that a little bit. They're thinking, but if they're negative, doesn't that mean it's slowing down? Not if they are both negative. Again, as long as the signs are the same, then the object would be speeding up. If the signs of acceleration and velocity are different, like they are here, then the object must be slowing down. Okay, the last question for this. What is the speed of the object at time t equals 5? So again, specifically talking about speed. Now, again, for those who aren't familiar with this, there is a difference between speed and velocity. As I was just saying on the previous question, velocity has direction. A negative answer versus a positive answer indicates a specific direction. Speed does not consider direction. So therefore, speed will never, ever be negative. So what that means then is, by definition, speed is equal to the absolute value of velocity. So if I want to know the speed of the object at time t equals 5, then what I'm really being asked to find, so speed when t equals 5, is really asking me to find the absolute value of v of 5. So remember, v of 5, that's going to be 20 minus 5 squared. That's going to be 20 minus 25. That's going to be the absolute value of negative 5, which just gives us positive 5. Now, the velocity was measured in meters per second, so the speed is measured in the same units. Again, what's going to make them different is that the speed must end up being positive. So the speed of the object at time t equals 5 is 5 meters per second. Okay, so that's all about higher order derivatives, and you'll see us come back and revisit higher order derivatives throughout this course. But moving on to the other derivative rule that we're going to talk about today, it's called the product rule. Now, yesterday when we were talking about basic derivatives, I mentioned briefly that the derivative of a product of two functions, unfortunately, is not quite as simple as just the derivative of the first function times the derivative of the second function. That would be incredibly too convenient, so of course it can't be that easy. So the product rule tells us how we can find the derivative of f of x times g of x. And it turns out to be the first function times the derivative of the second function plus the second function times the derivative of the first function. That's the product rule. And I am going to take some time here, and I don't want you to write this down, so don't worry about memorizing this or learning this. I want to just show you where this product rule comes from, because again, I can't emphasize enough that even though we're not actively using limits, all of these different rules that we're going to continue to learn are in fact based on using the limit definition. Okay, so here's the proof of this product rule. So again, we're trying to find the derivative of f of x times g of x. Well, remember, if we're using the limit definition, then that means we're going to have the limit as h approaches 0 of, now remember, it's going to be the whole function evaluated at x plus h. So that means we're going to actually have f of x plus h times g of x plus h minus the original function, which is f of x times g of x, and then all over h. Now, it's this second step that's sort of the head scratcher. This is the one that I'm going to show you a step, and you're going to wonder who on earth thought of that. And the answer is, I have no idea, but it's still going to be a necessary step. So what we're going to do is we're going to actually subtract a new expression from this in the numerator. But I can't just randomly subtract something out of nowhere. Like, I can't just take some number and just subtract 2 from that and say it's the same thing. So I have to undo that by adding it right back. So what I'm going to do is I'm going to subtract the quantity f of x plus h times just g of x. So again, very random seeming, but you'll see where I'm going to eventually go with this. So I'm going to subtract that, but again, I can't just subtract something out of nowhere, so I'm going to add it back. And then don't forget, we still have that minus f of x times g of x, and this is all over h. Now again, if you notice what I just subtracted and then added, those cancel each other out. So that is technically a 0. And because I've technically just added a 0, this is still equivalent to the previous function. Now the reason I did that, I'm now going to do a couple of things. So I'm going to group the first 2 terms over the denominator, and then I'm going to group the second 2 terms over the denominator. And because we are adding, I'm able to split this limit into 2 separate limits being added. Again, that's one of our limit properties from the previous unit. So what that then becomes is I have the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x plus h times g of x divided by h plus the limit as h approaches 0 of f of x plus h times g of x minus f of x times g of x all over h. Okay, so now why would I have done that? So now let's just look at this first limit over here for a moment. So in this first limit in the function, notice that both terms in the numerator contain an f of x plus h. So I'm going to factor out that f of x plus h. And I'll use a different color just so you can sort of see that. And that is going to leave me then with g of x plus h minus g of x. And again, this is all over h. Plus, in the second function, I'm going to do something similar. Notice that in the second function, both terms contain a g of x. So just like you saw me do before, I'm going to factor out a g of x. And that means I'm going to be left with f of x plus h minus f of x all over h. All right, so now I have the limit of a function times another function. And remember, that means I can take the product of those limits. Well, the limit now looks like this. So I have the limit as h approaches 0 of f of x plus h times the limit as h approaches 0 of g of x plus h minus g of x over h plus the limit as h approaches 0 of g of x times the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, look at these limits that I have. This first limit, as h approaches 0, what happens to f of x plus h? Well, that just becomes f of x times. Now, this limit right here, the limit as h approaches 0 of g of x plus h minus g of x all over h. That's just the limit definition for the derivative of g of x. So in other words, that's giving me g prime of x plus the limit as h approaches 0 of g of x. Remember, if your function's in terms of x, but your limit is dealing with h, then g of x is considered a constant. So the limit of g of x as h approaches 0 is just g of x times, and then finally, this limit here, this limit here, as h approaches 0 of f of x plus h minus f of x all over h, again, we should recognize that that's just f prime of x. And therefore, that is our product rule. Again, at no point will I ever ask you to come up with this proof again. I'm not going to test you on it, but I want you to be able to see that these rules really do come as a result of our limit definition. Okay, so we're going to find the derivative using the product rule. So here we have for part A, f of x equals 3x plus 8 times the quantity x cubed plus 3x plus 5. So in other words, 3x plus 8, that's kind of like my f of x from the product rule formula. X cubed plus 3x plus 5 is like my g of x from that formula. Again, I don't want to actually call this f of x because that's what this whole function is already called. But in terms of applying the formula, that's how you can think about this. Okay, so to use the product rule, we're going to do f prime of x. So the derivative of this product is. Now, watch carefully how I'm showing my work. So in some of these steps, I'm just going to show our intent to find the derivative, but not actually find it yet. So here's what I mean. So again, the first derivative will be the first function, so 3x plus 8, times the derivative of the second function. In other words, I'm just showing the actual application of the product rule, but I'm not actually evaluating it yet. So it's the first function times the derivative of the second function plus, I erased the derivative, plus the second function times the derivative of the first function. So that right there was showing the product rule. So now let's actually find that derivative. So we have f prime of x equals, so we have 3x plus 8. Now to find the derivative of x cubed plus 3x plus 5, we're just going to use our basic derivative rules like we used yesterday. So that's going to be 3x squared plus 3 plus, I've got my x cubed plus 3x plus 5 times, and then the derivative of 3x plus 8, well, that's just going to be 3. Okay, now we could clean this up a little bit. We could distribute, we could multiply, we could combine like terms. I believe that WebAssign will allow your answer to just look like this. So WebAssign will allow your answer to look like this. And for now, that's fine. As long as we're not actually doing any applications involving this function, there's not really much need to do anything beyond that. Okay, but keep in mind, eventually we will have a need to do a little bit more with simplifying this function. All right, and that's applying the product rule. Let's do another one. All right, so this time we have y equals x to the fourth times the cosine of x. So to find our derivative here, so y prime will be, okay, so again, it's going to be the first function, so x to the fourth, times the derivative of the second function, plus the second function times the derivative of the first. All right, so now we get y prime equals, so we've got that first, so x to the fourth, times, now the derivative of cosine of x, remember, is negative sine of x, plus, now we've got that cosine of x, times the derivative of x to the fourth, which is going to be 4x to the third. And finally, we're just going to clean this up a little bit. We're going to put y prime equals. Now that negative, I want to move that negative out in front, because putting it in the middle, even with the parentheses, it still makes it almost look like subtraction, which could easily lead to a mistake. So I do want to move the negative in front of that term. So this now becomes negative x to the fourth sine of x, plus, same thing here, this 4x to the third, we're better off moving it in front of the cosine of x factor. So I'm going to write that as 4x to the third cosine of x. And that's our derivative using the product rule. All right, so we're going to find f prime of x and f prime of c for the given function and value of c. So we've got f of x equals x times the sine of x. So again, we've got a product there. And the value of c we're talking about is pi. Well, to find f prime of c, to find f prime of pi, first I need to find the expression or the equation for f prime of x. So let's do that. Well, again, if this is x times the sine of x, we have to recognize that this will require us to use the product rule. So again, if you read the function in your mind at least, when you read it to yourself and you recognize that you're multiplying, that's when we should be using the product rule. So f prime of x equals, okay, so once again, it's going to be the first times the derivative of the second, plus the second times the derivative of the first. Well, that means I'm going to have x times the derivative of sine of x, which is cosine of x, plus sine of x times the derivative of x, which is just 1. And if I just clean that up, I've got x times the cosine of x plus the sine of x. So that is f prime of x. That's the first thing that they asked us to find. But now the question's also asking us to find f prime of c. And in this case, c is pi. So I'm trying to find f prime of pi. Well, that just means I'm going to substitute into the f prime of x that we just found. So that means I'm going to have pi times the cosine of pi plus the sine of pi. Well, that means I'm going to have pi times, now cosine of pi, remember, is -1. And then sine of pi is 0. And finally, that just gives me a negative pi. So now that you've seen higher order derivatives and you've seen the product rule, let's combine those two ideas together. So let's find the second derivative of y equals x times the sine of x. And you may recognize that that's the function that we were just using in the previous example. And I'm mainly doing that just to help speed things along here a little bit. So again, if I want to find the second derivative, in order to do that, first I have to find the first derivative. So that means my first derivative, again, because you just saw this work, I'm just going to race through it, but I don't want to just skip over it. So again, it's going to be the first times the derivative of the second plus the second times the derivative of the first. That means I'm going to have x times a cosine of x plus sine of x times 1. And then finally, I can write that as x cosine of x plus just the sine of x. Now, that's the first derivative. The second derivative means I need to find the derivative of that function. But now notice the first part of that function is another product. So within the second derivative, I'm going to have to find another product rule plus the derivative of sine of x, which is just going to be one of our basic rules from yesterday. So let's start with that. So the second derivative will be the derivative of this product plus the derivative of sine of x. Again, that's just using our basic derivative rules. Remember that the derivative of the sum of two functions is the sum of their derivatives. But now that first derivative is a product. So I need to now recognize I need the product rule. So again, it's going to be the first times the derivative of the second plus the second times the derivative of the first, and then finally plus the derivative of sine of x, which is cosine of x. And in fact, let me just put those in a different color just so we can see that that's a different part. Oops. Does not want to cooperate. All right, there we go. All right, and then to finish off the first part, now we've got y double prime equals. So that's going to be x times a negative sine of x plus cosine of x times a 1 plus cosine of x. So now I've got negative x sine of x plus a cosine of x plus another cosine of x, which hopefully we all recognize can finally be written as y double prime equals negative x times the sine of x plus 2 cosine of x. And that's our second derivative. All right, and we're going to wrap up this lesson by looking at one more type of question that the AP exam is particularly fond of giving. So because we are going to learn lots of different derivative rules throughout this course, one of the ways that the AP exam does enjoy assessing that you know those rules is by doing doing examples or problems like this, where you're not dealing with the specific function, such as the ones that you saw previously, but you're dealing with generic functions where they're really just trying to zoom in on just the rule itself. They don't want you to get bogged down in a particular type of a function. They just want to make sure that you know how to apply the rule in general. So, given g of 1 is 8, g prime of 1 is negative 5, h of 1 is negative 2, and h prime of 1 is 4. We're going to find f prime of 1 if. So now they're giving us these functions for f of x in terms of g of x and or h of x. And we have to apply whatever derivative rules are necessary to answer this question. So for example, on part A here, it says f of x is g of x minus 3 times h of x. And again, in order to find f prime of any specific value, first I need to know f prime of x. So let's start by finding that. So f prime of x equals. Now think back to your basic derivative rules. If I'm taking the derivative of a function that's the difference of two functions, then that's just going to be the difference of their derivatives. So that means it's going to be the derivative of g of x, which is g prime of x, minus the derivative of 3 times h of x. Now that is a constant times a function. And another basic derivative rule that you saw is that the derivative of a constant times a function is the constant times the derivative of the function. So this is what f prime of x turns out to be in terms of g of x and h of x, or more specifically in terms of g prime of x and h prime of x. So now I can find f prime of 1, so that's going to be g prime of 1 minus 3 times h prime of 1. But now, remember we were told that g prime of 1 is negative 5. minus 3 times, we were told that h prime of 1 is 4. So I've got negative 5 minus 12, and that gives me negative 17. Same thing for part B. Okay, so to find f prime of 1, first I need to find f prime of x. Well, this is a product, and we've just been working with the product rule today, so f prime of x will be g of x, the first, times the derivative of the second, h prime of x, plus the second, h of x, times the derivative of the first, g prime of x. So that means f prime of 1 is going to be g of 1 times h prime of 1 plus h of 1 times g prime of 1. And now when I substitute all of those values, so g of 1 we know is 8, h prime of 1 is 4, h of 1 is negative 2, and g prime of 1 is negative 5. 8 times 4, that's going to give us a 32, plus I have negative 2 times negative 5, and that's a positive 10, and finally we get 42. All right, so again, these types of problems are very commonly found on the AP exam because it gives them a chance to make sure that you know how to use these derivative rules without the chance of you getting bogged down by a specific type of function. All right, so again, today we've talked about higher order derivatives, first derivative, second derivative, third derivative, and how that also specifically pertained to position, velocity, and acceleration. And then you were introduced to the product rule. Again, I cannot emphasize enough that the derivative of a function times another function, it's not just as simple as the product of the two derivatives. So make sure that you work on memorizing that product rule. All right, good luck.